Hi, everyone. So, um, so far, I think this has been a very exciting conference, and I hope it continues to be exciting. I'm starting to apply pressure on the speakers again. Uh, the next up, we have Pia Zacharias. Pia comes from Statkraft, which is, I believe, the largest hydropower company in Norway. If you don't know, almost all of the power in Norway comes from hydropower, except in Svalbard where they burn coal, which I think they get out of a mine that's run by the Russians. And if you really want to know all about World War I politics, you can read all about Svalbard, also known as Barentsburg. Anyways, that has nothing to do with what Pia is going to talk about, but maybe a little bit of Norway trivia. So, well, without further ado.
Thank you. Good morning, everyone. Also, thank you for inviting me. I agree with John. This has been a really exciting conference so far. So I hope to keep the excitement up when I'm talking now about predictive maintenance and hydropower. My name is Pia, and I work for Statkraft, which is actually not just Norway's, but Europe's largest producer of renewable energy. Actually, 97% of the energy that's produced is renewable. Statkraft is 100% Norwegian state-owned, but it has expanded now into over 20 countries with more than 6,000 employees. And Statkraft owns or partially owns and operates almost 400 power plants around the world. And this is a map that's supposed to show the entire portfolio of assets that Statkraft owns around the world. So the focus in the past has been mainly in Europe. And there it's also hydropower, which is probably the dominant energy source, especially in the Nordics. There it's more or less just hydropower, some wind. But then more recently, there are efforts ongoing in South America and also in India. So the company has been growing quite a lot internationally recently as well. So today I thought I would give a slightly different talk maybe to what we've heard before. I'm going to talk more about a journey that we've made at Statkraft towards what we call predictive maintenance. And I can warn you, we're not quite there yet. We're taking baby steps towards predictive maintenance. So the whole talk will be centered around challenges that we encountered, use cases that we have been looking into and that we have tried to scale up, and formulate in a more generic approach. I'll briefly talk about the platform that we've built. That's a kind of in-house development, a machine learning platform that is running models across the entire hydropower fleet. And every now and then I will point out some learnings that we've made along this journey. So, predictive maintenance. It's a big topic. I think it's discussed widely in this branch of business. However, the state of the art nowadays is planned periodic maintenance. And that means we're kind of close in time to the actual failures that occur. So we're not yet actually in a position to make predictions based on all the data that we're collecting in the plants. And I'll try to, maybe from my perspective, give an understanding of why that is, and what needs to be done in order to actually achieve the state of predictive maintenance. And in this plot that you see on the right, you can see the different stages, the different time spans that I keep talking about and referring to. So when we think about failures, the further to the right, this is a time axis on the x-axis, the further to the right we get, the closer to the failure we are. When we talk about reactive maintenance, that's probably when things are too late. The failure has occurred, things are broken, you have to go in and fix everything. But then if you move further, well, actually now this is going backwards in time, but you go further back in time from the failure, I guess the more you invest into analytics and especially predictive analytics, and the better off you are, I would say. So you want to keep your assets alive. You want to be able to schedule maintenance in a smart way, not necessarily just according to a fixed schedule. And you want to do an access. You want to develop clever tools in order to get all that information and collect it in a convenient way, make it accessible to, for example, the people at site, the maintenance teams. Okay, one of the issues with hydropower, I think it's a good one, is that the plants, they live for a very long time. So typically 50 to 80 years is what you call the lifespan of a typical power plant. They're also characterized by relatively low operation and maintenance costs, and that's around of the order 2 to 3% of the total cost of the plant, all the money you invest into the plant. So that's actually, it is very low, but if you think about the big revenues, it's still quite a lot of money that's invested here. And of course, if you move to more and more predictive methods and analytics, there is quite some money to save here. There is, of course, always, from a company perspective, a desire for more optimized performance and increased efficiency, but also nowadays, most likely, flexibility would be an important issue that can be addressed with more predictive methods. So you would ask the question, why aren't we quite there yet? And I think, there's quite a lot it takes to get to that stage, and some of the requirements are shown here. We need to be able to measure and store all of the relevant sensor data that we're collecting in the plants, and we need to make that data available in real time. And this is now in a production setting. This needs to be accessible for everybody who needs to actually then work with the data or the predictive parts of it. So ideally, you want to not just show the data, but also leverage from it. So you want to build advanced methods and combine domain knowledge and historic events that have happened. And you need to do that somewhere, so you need to build up monitoring services or platforms that aim at doing more advanced failure diagnostics, short and long-term predictions, and eventually you may be able to do residual lifetime investigations and future risk assessments. That's something the business side always asks for. So maybe the final state of such a platform could be that future risk assessment. Benefits of condition monitoring, or kind of like using this along with predictive analytics. It's kind of similar, I would say. But the main benefits are to extend the asset life. So by monitoring the components carefully, avoiding big failures, you can definitely extend the lifetime. Minimizing downtime, which happens due to unforeseen failures, for example, or also during scheduled maintenance when you realize something odd has happened and you need to also exchange another part of the equipment which you didn't plan for. Reducing O&M costs, that's also That kind of makes sense. Maximizing production in the sense that you can actually, through careful monitoring, also operate your machine in different regimes if you then know what you're doing and you're carefully monitoring. Yeah, I guess better maintenance, planning and logistics, and reducing the costs that are connected to regular inspections that are not necessarily, that you don't necessarily have to actually perform. They can be reduced. Yeah, so when it comes to the more data-driven approaches and analytics in hydropower, we have encountered quite a few challenges that we didn't necessarily expect when we looked at the data for the first time. And I'll try to sort of categorize them here a bit. By the way, this is a view of a power plant. I'll get to that on my next slide. But let's first talk a bit about the data and the analytics we want to do with it. When it comes to failures in general in hydropower, these are not very common. So that's a bit of a dilemma if you want to train machine learning models on failures that you don't actually have. So the main components, there is barely any failures. I think over the last 10 years we have maybe had 10 bigger failures, nothing dramatic, but still way too little to actually do big failure statistics. Most of the failures that we do observe in the equipment happen in the auxiliary equipment. So these are, for example, pumps or like the cooling system. So yeah, parts of the equipment that are not crucial and therefore don't necessarily have a lot of sensors with them. So yeah, you're in this dilemma. Either you have those main components with a lot of data, a lot of sensors, very few failures. And on the other hand, you have all the auxiliary equipment, which you don't really monitor with sensors, but there you have most of the failures. We also have to take into account that hydropower plants are rather unique. So I would almost dare to say every power plant is different. And they differ in kind of like all aspects, from the kind of turbines. You see an example on the upper right. The kind of reservoirs, the waterways the power plants are connected to, but then also the suppliers of the generators might differ, or even if you have a power plant that consists of 3 almost identical units, like shown in the picture on the left, you would expect them to behave very similar. Unfortunately, they don't. That can have very different reasons, from the mounting of the sensors to small differences still in the equipment, even though it's the same supplier. So you can never actually be sure that you have equipment that is as similar as you would like it in order to compare easily between units or different power plants. Data quality, we all are aware of that, I hope. There's one more thing that's kind of maybe a bit more unique to the kind of data we're looking into. There is a lot of data that has been collected over time. Typically, over the last 20 years, people have collected data, sensor data from the plants. However, they have not really thought of it as to be used in analytics. It's been mostly collected for it to be collected. I find that a bit strange, but yeah, we sit on a lot of data and no one ever has looked at it, and it hasn't been looked for checked for whether it's useful for analytics. So yeah, you hear there's a lot of data, you have great expectations, but then the data turns out to not be useful at all due to many different reasons. We don't necessarily have information structure for all the sensors we're collecting. So when you want to scale up and you have found a nice model for one failure mode and you want to implement that model in another power plant, it happens to be that you can't find the same sensors because you don't have that information model built around all the sensors that we have data for. data acquisition and the data flow until you actually get hold of the data. That's often a kind of mystery. So you need to be aware of all the filters that have been implemented in the different systems, and it can be a bit tricky to actually work with the data if you don't know about all these kind of filters that have been applied. And things like high-frequency data, people are not really, haven't taken that into account from the start when they start building the data platforms. They haven't necessarily looked into high-frequency data or thought about it. And the last point on this list, it's not necessarily, but a bit connected to analytics, I would say, is the way people are used to work or have been working so far. This is not necessarily a data-driven environment, because people are more used to walking around in the plants, listening into the equipment, like touching it, feeling the vibrations, and sort of like having a very close connection to the plant itself, but not necessarily looking at it from a data perspective. So when it comes to implementation of more advanced models, they can be a bit maybe reluctant or not necessarily, it's not kind of in their mindset, so you have to sort of also convince them, build up trust, communicate around that, and make those algorithms accessible for them, so they can actually, you build up a new kind of relationship, a new way they work. You're building a product for them in the end, so it's kind of important that they want to also integrate it in their way of working. And that's just one example how people would probably feel connected to their plant. They usually, they do that a lot when they walk around. They touch their equipment and they make sure it feels like it always feels. Otherwise, they get worried. A brief introduction. Maybe that slide could have been a bit more to the front, but just the typical hydropower plants in Norway. How do they work? They are usually mountain power plants, meaning the hydropower plant sits inside a mountain, whereas the reservoir is somewhere on the top in the mountains, and the water is channeled through tunnels and pipes into the mountain. Where you typically then have a vertical construction with a turbine on the bottom that spins as the water falls onto it. It rotates the shaft, which you see here. And then further up, you have the generator, which is rotated by the rotating shaft. The inner part of the generator, the so-called rotor, is spinning as well. And in the outer part of the generator, in the so-called stator, you produce a magnetic field and currents, and through that, eventually, electricity. These are a few impressions of what it looks like in a typical mountain power plant in Norway. So usually you drive into very long tunnels, several hundred meters long. Towards the end, you reach that so-called machine hall, which is the uppermost level of the hydropower plant. Here you see a power plant with 4 almost identical units. These are like the tops of the generators, if you remember the picture I just showed, so at the very top of the construction. And then when you go down in this, it's almost like a huge building inside of the mountain, several stories high, and when you walk down the stairs, you get to the different floors with the generator, the shaft. This is the main inlet valve where the water comes floating into the power plant, and you also see this valve which is moving and opening and closing, letting the water into the plant. This is an image of a generator that has been taken out of operation, and this is the inner part of the generator. I would call this like the heart of the energy production. This is the rotor that spins. It's super cool to look at these and for real. They're massive constructions, and I think around 300 tons. This is maybe 200 tons, and this is another 100 tons. So huge constructions that don't come in one piece usually. So this stator construction, when you open it up, it looks like this. These are the stator bars. This is where the magnetic field and the electricity magnetic field and electricity is produced. So the stator bars, this is, they are kind of like crucial here. This is also an example of one of our first use cases now, which I'll present, and then I'll present a couple more. So here they actually had a failure. A small stator bar smoke development, maybe fire, and they had to open up this stator in order to investigate the root cause. And that caused a long downtime, which actually gave us the chance to step in and do some analytics. It takes around 2 years to replace a component like this. So they basically had the chance to not run it for 2 years or take it back into operation and run it with a lot of monitoring on top, which is what they decided to do. So this unit was equipped with a whole bunch of sensors along these so-called, they're called core joints. These are the places where the stator is like bolted together. It comes in 2 or sometimes 3 parts. And those are like the most sensitive parts when it comes to vibrations and maybe also temperature increase when something is wrong. And a lot of deformation can potentially happen in those places where the unit is bolted together. Yeah, but this is kind of where we started with one and later on several of our use cases, adding additional sensors to the already existing ones, then carefully monitoring these sensors, first with more simple models, but then we would like make them more and more generic, so we could also roll the same kind of model out to other units and other power plants. And this was actually quite, I think, beneficial, a mutual benefit, both for the business, but also for our, what we called back then task force for advanced analytics. So by carefully monitoring the sensors when the unit was put back into operation, we could actually sort of give hints to the root cause, help them with the root cause analysis, which was connected to a deformation along these core joints. And that was due to also the cooling system not working as efficiently as it should have, leading to increased temperatures at the top and the bottom of the stator, kind of what's indicated in the CFD simulation here. So there were a lot of things we could help them sort of pinpoint to and closely monitor over time. So we would eventually build a platform around these models, but we first started with these very generic approaches of like monitoring vibration peaks, monitoring differences in temperatures, and then monitoring trends on vibration peaks, and so on. So just building this up step by step, also in very close cooperation with the people at site. And in this particular example, we were able to keep the unit alive for another 5 years. There was a new generator waiting to be installed in the meantime. You see it on the right picture there. But since this monitoring went on so well, and also the energy prices were so high during the last couple of years, it was worth for them to wait until the actual, we could basically run the unit to end of its lifetime. This is just another kind of illustration how we try to approach our use cases in the from then onwards. So from looking into symptoms, we would try investigation and testing around the problem, try to help with the root cause and failure development analysis, build up monitoring around those failure modes, and then sort of identify other similar failure modes across the fleet and run the same kind of models in other power plants. Let's continue with another use case that is a bit more of an R&D kind of project that we followed up on, and that's connected to audio analytics, sound. And why did we decide to look into sound? There's several reasons why this could be relevant for hydropower. Some of the smaller power plants, for example, they are not usually staffed, and sometimes they are hard to reach. So having a small installation there where you can basically just listen into the sound, that was considered to be very useful from the maintenance team side. Also, while we are talking and working together with the technicians and maintenance teams, we noticed that they go in and listen to the plants, and they do hear when something is off. They would point us to a unit that is different from another unit. So that was kind of how we came up with the idea. And then we would try to actually understand whether this is useful for making predictions as well. Yeah, maybe one other motivation of some places that you really cannot get to easily. I think the pictures are quite convincing. This is not a power plant. This is a water intake area up in the mountains. It's called the window. And it's actually the water intake of one of the big glaciers in Norway. And places like this are only reachable by helicopters. So when they built this, back in the days, that's how it looked like on the picture on the right. This must have been quite a hassle, and they don't really have any kind of monitoring up there in the mountains. So that would also be a nice use case. We didn't go there. We were not allowed to take a helicopter and get to these nice places, but I should change the order of this slide. I'll come back to that, I'm sorry. We went to another power plant up in northern Norway. It's also a kind of special one because that one basically it shuts down during winter due to the snow. You cannot get there by car during winter, so they take a snowmobile to get there. And their wish was also to have some kind of installation to basically just listen in. Not to do necessarily fancy analytics, which is something we tried in another project, but just to be able to listen in during winter because there's no one there. Which is also nice if you think about surrounding noise, which could potentially disturb your recordings. In those power plants, no one is disturbing you during winter. So what we did here, we put up a small device, a Raspberry Pi, connected it with 2 microphones. I'll show you on the next slide how that looks like. Set up a small audio interface. We stored the data first on a local hard drive. Then we had good enough internet connection. We pushed the data to the cloud, and from there transferred it back into our machine learning platform. I'll also come to that. This is our super quick and cheap installation. If you remember the previous slides where they actually had to open up a stator and install sensors and take the unit out of operation, or it was out of operation for several months, this installation takes an hour. So it's a very non-invasive method of just going there and getting some quick information on a place you don't get to easily, or you don't usually have staff there working throughout the year. And then the idea here was to combine that data, the sound, and now this is basically just, this is nothing fancy. This is just the loudness, so it's kind of like, an RMS-based, it's the RMS value that we're using here to derive the loudness. But it kind of, gives you a very nice impression of what you can do on top of this. You can combine it with the operational data, for example, the power, which I think is shown in green here. Yeah, it's in green, and the RPM, the rotational speed, so when the unit starts spinning, is shown in red. So in this particular example, we can now listen into a start, and maybe this even works. It's kind of nice to listen in. I don't really see my mouse right now. Nope. It was there for a second. It's there again.
Try spacebar.
No. See if I can. No.
Can I try?
Yep. Thank you. Let's just listen into that one. So this is now the sensor which we put onto the main inlet valve, the picture on the left. And they're opening the main inlet valve. And the water comes flowing in. And now you also hear the unit spinning and the water running. And this is actually now, it's a contact microphone. This is something we also learned when we played around with different microphones. Contact microphones are quite nice when it comes to listening in and at the same time having something that is undisturbed by the other units. So earlier we had a project where we put up microphones in the machine hall, and it was several units running sometimes at the same time, sometimes only one unit running, sometimes two units running, and we were struggling a lot with just distinguishing the sound from the different units. With a contact mic, or first with a single unit, of course it becomes much easier. You don't have a lot of neighboring sounds. We don't have different units. But with a contact mic, you don't necessarily catch the noise of all the auxiliary equipment. You're very close to the actual source of the sound. So we found these types of microphones to be very useful when it comes to like monitoring something that's closer to like a vibration signal, but you could still like listen in as we just did in the sample I showed. See if I can go back to my other slides. Okay, and now I just briefly wanted to go back here. In a more of an industrial-like setting, we have worked together with Expert Analytics on a kind of more prototype-like version of this approach, which I think they have now turned into a product, which they also call Edge Audio Analytics. So that's a bit of a more, I would say, a more advanced industrialized approach, where you can actually do anomaly detection on top of the sound, which is similar to what you just heard, but you would then do some kind of maybe classification on the type of anomalies that you find, maybe also in different kinds of equipment like transformers, or you could like put the microphones again close to the core joints, which is an installation that we see on the upper right. I think in the picture next to it, we tried to record something. This is the excitation unit of the generator. So here you have like coal brushes that are wearing off over time. So we tried to also follow up on whether we could like listen into changes over time. So this installation lived for quite a while, and we found quite a lot of interesting features in the audio profiles. And the way we kind of worked with the data was that we did the processing and the training on edge at site. Again, had a very quick and easy installation, and then only transferred anomalies to our machine learning platform. Okay, I think I'll go back here. Yeah, and now I come to the last series of slides. This is actually the platform that we have built around the use cases. I'll show one more after that, I think. Kind of coming back to the idea why we're doing this and what are we trying to achieve here is that we actually are trying to make this useful for someone else. This is not what we're using for us, not as data scientists, not as developers, but we're actually building this for discipline experts, maintenance teams, technicians who are working in the power plants, who want to understand if something is off or happening to the equipment. In that case, sensors on some failing equipment maybe. So we want to help them, and we want to make this intuitive for them. And they don't necessarily want to know the details of our machine learning models either. They want to know if something is wrong or not. So in this approach, we try to combine kind of like machine learning platform with a dashboard solution, because that's kind of what they want to see. They want to pull up a dashboard, which is hopefully even like pre-built, so they don't need to interact a lot. And they want to see if something is off. They don't want to go into a model report and understand if this is wrong or not. They want something to tell them what to look into. They don't have time to spend on analytics. So that's the part we do, and then we present our work in the most intuitive way. And I think we found a very nice compromise by combining the machine learning results with the operational data in this platform. The way we have integrated the models is also a kind of fully automated approach where they kind of choose models from a drop-down list. They can schedule the model runs to happen once per day, once per week, once per month. They choose the time period, they choose the model, they choose thresholds for the anomalies, and that is all then presented for them in a kind of dashboard solution. And in that dashboard solution, we have also built up a system for automatic notifications and alarms. So if something happens on a sensor value they're monitoring and a threshold is breached, for example, they will be notified. They don't even have to go into the dashboard, but they will get an SMS or an email or whatever their preferred way of notification is. But of course, they can also go into the platform and check on other sensors and try to understand what's happening. The backend that we built, as I said earlier, it's an in-house development, so we have full control of the whole package. We have containerized all the services that are running in the background. We're moving the platform right now to Kubernetes. This will be relevant for the scaling. We're rolling these dashboards now out across the entire hydropower fleet. That's around 200 rotating units for the hydropower part that we have been looking into. But it's also a platform that's built in a technology agnostic way. So we're using this also for wind parks at the moment, especially the models, because there's even way more data for the wind parks. And they are struggling with organizing the data in a nice, comprehensive way. And I think our dashboards are quite useful for them as well. And one more thing that was asked for and desirable from the maintenance perspective was to have a support for phone or tablet view, because the way people like to work nowadays is they don't necessarily just want to sit in front of their laptop or a big screen, but they want to take it with them, take the information with them on a tablet or a phone, so they can kind of do the guy did in this first picture here. I don't know if you saw that, but he was, where was he? He walks around with his tablet, and at the same time he goes and checks on the sensor, which has maybe just triggered a threshold. So that's kind of how we envision them to work also with the kind of results from the models that we provide. Okay, do I have more time?
You have 7 more.
Great. So then I'll just briefly comment on, give a bit more into the detail on the kind of models that have proven quite valuable so far. Some of these are generic and work for all kind of technologies, I would say. Some of them are more tailored towards specific technologies. We have some machine learning models here as well. They're hidden under rather simple terms. For example, this health model is a gradient-boosted quantile regression model, but we don't really say that to our users, but we do present them with kind of traffic light view that we have on the lower right, which can potentially give them all the information they want to have, but also gives them as little as is needed in a kind of traffic light. So if the health model triggered an anomaly, and that anomaly is above a certain threshold, which can be chosen automatically, or they can set it, you get a red traffic light, and you ideally check. You can also follow up on your anomalies by pulling up a trend, which appears then underneath the traffic light. You can do that for every single model you have set up. You can click into the individual points and then get a more like, I would say like more comprehensive view of all the input time series that were used as predictors. You also got more information on the training data, et cetera, et cetera. So with this, you can dig into the details, which also makes these models quite explainable, I think. But you don't necessarily have to. If all you want to know is whether things are good or not, you just look at the traffic lights. That's one example. We have more tailored models, such as start-stop analysis. That's usually relevant for them, just counting everything, doing like statistics over the way the machine has been run, look more into the start sequences, how long were the starts, how many were there, were they okay, were they odd, were they whatever. But these are more like then tailored approaches, like the audio, or there's a lot of also vibration analysis happening. And we can also connect to like other data sources here, like I showed for the audio, or vibration data analysis is another good example. Oil lab results are something we get from external providers, which we then also ingest as a model into the platform. And this would be maybe one last use case that we have, I would say, kind of solved with our health model. It was a thrust-bearing failure that occurred in one of the big plants up in the north. And then when they had this failure and disassembled everything, they put in additional sensors and took it back into operation. It takes a while, several months, if you have these rather, bad failures. But the nice thing with these additional sensors was that we now had a kind of comprehensive data set that we could actually use to train our health model, which we did. And in order to prevent the same kind of failure, we started monitoring all the sensors along the shaft, including all the thrust-bearing sensors with the kind of health model I showed before. And after a few weeks of training and making predictions, that model triggered again. And it triggered pretty much 4 weeks before any of the alarms in the so-called SCADA system. That's kind of the system that the dispatch centers are handling. That's shutting the plant on, or it's shutting it off if something strange happens, but it's like a threshold-based system. It's very crude for analytics, so we don't work with that system. But that system would shut the plant down. We were about 4 weeks earlier than the actual alarm that triggered and shut off the plant with our anomaly models, the kind of health models I showed earlier. And we could send out early warnings to them. They were kind of prepared for the failure to happen. They saw it coming. They weren't quite quick enough to react. They had scheduled maintenance on the thrust bearing, but the failure occurred the night before. But the good thing about this is that we could actually prove that the models we are running, they can be quite useful to avoid bigger failures. And I think also by running the models in this way and working in close collaboration here with the maintenance teams and following up on the trend development, making the models explainable, we have been able to build up some trust. They had scheduled maintenance when we notified them about shifts in the models. I think we are one step ahead of this stage. We have built up some trust in the models, hopefully. And to conclude, I just wanted to comment on one maybe small thing we're doing, but it kind of connects back to where I started. When I talked about the data itself and what we're kind of challenged by when we look at data, at least on the hydropower side, there is not necessarily a good structure around that data, and that needs to be changed in order to make digitalization work, in order to make predictive analytics work. Also, in order to roll out dashboards across a fleet, you would ideally have an information model behind all the data, so you understand the data right away and don't have to actually search for every single sensor that you're interested in. And there are some efforts ongoing now. It's a big project that looks into structuring the data based on an information model that Statkraft is helping to develop. It is also an ISO standard, so hopefully more and more suppliers will adapt it as well. When we learned about this effort, we thought it would be a great use case to try some generative AI. And we have, basically ingested data into a transformer model. So we're using one of the GPT, I think, 4 series models, and we fine-tune those models with the training data set that we have built up. So we kind of, we fine-tune an existing large language model with example data that we have collected. We do create a custom large language model for that purpose, and we have deployed that model, and now people are using it to map more data. So eventually this will, I think, be very useful, not just for the data we're structuring now for hydropower, but also for other technologies, and maybe also for hydrology, when we think about all the reservoirs that are connected and the waterways that are sort of giving us information about water inflow, and then the entire energy management cycle that comes on top of that. So there's like huge potential to extend such models also, and fine-tune them for other technologies. Okay, I hope I finished in time and I didn't bore you too much. I think this was an effort, an attempt to describe how we're trying to move towards predictive analytics, maybe still a bit on the preventive side here, but definitely started to move or to invest into some more concrete use cases, building up platforms, trying to structure the data. Also trying to build up trust in those methods by onboarding a whole bunch of other teams, other maybe even departments and people at site. I think personally that it's very important that we communicate around this, not just in the department where we typically work, but also across the company, and also have nice collaborations in R&D project with external research institute and universities. I think that's all I have. Thank you.
So are there questions for Pia? Thorsten. I'll start with Thorsten.
So for more complex sort of object like airplane engines, people are using these full-blown digital twins, right? Where you have a much more sort of physics integrated monitoring system. And I can think of a number of reasons why this would be total overkill here and why it might be complicated, because you have different hardware and you don't have the sensor streams. But then like for wind turbines, right, presumably at least there you have lots of the same. So are you then also exploring like physical representations to sort of see how, you know, different sensors might make a lot of sense, and then you can run a simpler model? And so how do I think about sort of the trade-off between like having a full-blown simulation? When does that even make sense? And when do I just want to approach it empirically, I guess? What are sort of the trade-offs?
Right. It's a very good question. I think there's like a big difference, as you also said, between wind and hydro, because wind turbines, you have up to 50, 90 turbines in the wind parks, and they're almost identical. Hydropower, very unique. So we have seen or even joined some smaller digital twins efforts and like really small plants that are not like connected to any of those bigger systems. They're kind of standalone power plants, and they're testing it. But I don't really see that this is something that people react to when it comes to scaling. But there are efforts ongoing for hydropower. I don't know where they will lead. For wind, it makes perfect sense. This is something that will develop in the future, I'm pretty sure. Because it makes sense, as you say. This is super scalable, and you have several almost identical turbines in the wind parks. Yeah, there I see potential. It's coming.
Might be very nice, thanks. So I have two quick questions for me. First one, you showed like that you had the microphone system, and there was like this contact microphone, and another one it seemed to be just standing in the room.
Yeah.
Do you get different type of information from both? Do you correlate it?
Yeah, we do correlate it, and the information you get and the sound you get, it's very different. I can show you later. The two recordings are very different. So in the machine hall, you also have very different, like the environment. It's an open hall. You get a lot of like sound from auxiliary equipment, like the coolers, and you're never really sure what you're listening to. It's very noisy in that sense. So especially in the plants where people are coming and going on a daily basis, it's very tricky to actually understand what you're listening to. Also without like contextualization, like the operational data, is the unit running? Is it not running? Is another unit maybe also running right now? You get easily lost, I think. With the contact mic, it's a bit easier because you remove a lot of the surrounding noise. You're using it more like a vibration sensor, I would say. It's very similar to a vibration sensor.
It's less sensitive to someone walking on the room.
Yeah, it won't disturb your signal, I think. Yeah.
And I know that some people that are working on machine learning using like audio data, sometimes they first, if I remember right, make a spectrogram of the data so that you made an image out of that, and then you can use like a pattern recognition libraries that are developed for images to compute audio. Is this like something similar?
This is definitely one of the main approaches. You calculate, Fourier spectra, and you do, feature detection or build up feature databases around those, around the power spectrum and all the features you can extract from that, and do anomaly detection on those features. That would be one, approach to run anomaly models.
Right. Okay, super, thanks.
Hi, Pia. I have a question, or actually, if you have a comment on like the signal to noise ratio in like doing this in hydropower plants, because I guess hydropower plant engineers, they hope that faults will never happen, but I guess you dream that they will actually happen, so you kind of get some more signals, like fault signals, into your model, so you can actually do predictions. So how do you go about with this fundamental challenge that how hydropower plants basically never fail?
They never fail. Yeah. Yeah. So since we have so few failures, we don't train on failures, right? But we do a lot of investigation when it comes to understanding the failure development, because once you've had one failure, you can still kind of like learn from it, right? So a lot of our thinking is kind of centered around how did this develop? And if you understand the development, we don't want to like see that development ever again. So we built the models around detecting such developments, let's say a long-term trend in the vibration signal during the starts. We tried to set a threshold on the vibration peaks during the starts because we have found them to increase over time before something failed. So we kind of like take this reverse engineering approach to learn from the failures still, but not like really train on the failures, if that makes any sense. That's one way to approach it. But of course, we also get a lot of like input, which is maybe more physics-based from what people know about their equipment. So they would sort of point us towards correlations. Correlations are big. People are usually, that's the most relevant thing, I believe. They look into power versus temperature, power versus vibration, because that's kind of how they're usually looking at their data, right? They don't want a trend to change, so they don't want a correlation to change. So if they just have means to check in how the data evolves over time, and they already know what they want to see and what they don't want to see, then we can sort of like implement that in a model as well. So we would, for example, in a correlation plot, visualize the historical trend based on quantile relationships, and then implement like thresholds on the life correlation, kind of. Does that make sense? But do you get my point, or was that too confusing? Yeah. So kind of you learn from the way people are used to work, and then you can still build like simpler statistical models around that. Another approach. But it would, of course, be much nicer if we had like more failures. And it's not that necessarily we have few failures, but sometimes we have few failures in the sense of that they are not like labeled well. We might have a lot of repeating failures, and now I'm thinking about maybe wind turbines, and those failures are not like noted down properly. We don't have a failure database, which would be awesome to have if you do that on a big scale, and you have like thousands of sensors, typically 2,000 sensors per wind turbine, and then you want to just do, failure statistics on that. It's impossible right now because we don't have a failure database. So you have to invest a lot of time into extracting those failures, and that usually happens by talking to people who have noted failures down on paper somewhere or not. So a lot of effort goes into that investigation as well. And that will hopefully also be improved over time if you make people aware of it. But I think they first also need to like understand that this is an investment they need to take if they want to like digitalize the entire process.
Okay, are there more questions? No? Then let's thank Pia once again. And so now is the lunch break.